Hello and welcome to another very entertaining video. I wanted to take just a minute to go over some of the nuance of the half-life decay formula that we use to calculate half-life when it comes to radioactive decay. It's a standard half-life formula, it's just exponential decay. There's nothing special about it. But I think when we start throwing logarithms in, especially natural log, people can't remember back to their 8th grade algebra to know how to do this. So let's write out the formula. And embedded in this formula, there are actually 4 different variables that we could solve for. So let's define the variables. As written, the equation solves for n. And n is just the current amount of, in our case, radioactive material. And it could be in whatever units, as long as the units are consistent. It could be in grams, it could be in pounds, it could be in counts if we're using a Geiger counter. It doesn't really matter. It's just what we have. Then if we look at n naught, this would be the original amount. The other variables are t. This is simply time elapsed, and t half, which is my half-life. Now, I do want to make a note. The half-life is a constant for whatever we're talking about. It's different from element to element. The half-life of carbon-14 is different from plutonium, which is different than, whatever other thing we're looking at. But carbon-14's half-life will never change. It's determined empirically, and it's a constant. Now, some of you might be looking at this saying, well, what about E? I don't know what E is. Isn't E a variable? And the answer is no, E is not a variable. E is what's called the natural base. And it happens to be an inverse of the natural log. And it's actually just a number. I don't want to go through too many significant digits, but E is simply 2.71. A is just a number. So if I took the log of that number, I would get 1. And that's the idea behind this. And it's understanding E and natural logs. That's what's going to give us the key to solving these equations. So I think it's probably worth our time, before we even throw in numbers into any of these variables, just to solve the equations algebraically for each of these variables. Of course, as it's written, we solved for n. Solving for n naught is just a matter of dividing both sides by e and its exponent. So n naught would simply be n divided by e to the negative 0.693t over a half-life. But what about solving for t? Well, I can walk you through that process. That gets a little bit more difficult because it's embedded in that exponent to e. But remember, the relationship between e and natural log, these are inverses of each other. And so because the natural log of e is 1, then they kind of cancel out, and what I'm left with is just the exponent. Let me show you what I mean by that. Going back to the original equation, what we want to solve for right now is t. And you could use the same strategy with just a few variations to solve for the half-life, t half. The first thing we want to do is we want to isolate e. So let's divide both sides by n naught. Of course, that means on the right side, these cancel each other out. And what we're left with is n divided by n naught equal to e raised to the exponent 0.693t divided by t half. Now, to get rid of the exponent, all we have to do is take the natural log of both sides. So now we have the natural log of n over n naught is equal to the natural log of e raised to its exponent. And again, because these two things are inverse of each other, they essentially cancel out, which means now that the natural log of n over n naught simply equals what was in the exponent, negative 0.693t divided by my half-life. So continuing over here, if we were to solve for t simply equals the natural log of n over n naught times my half-life, all divided by negative 0.693. And like I said, with some slight modifications, you could solve for half-life, t half, if you wanted to. But that shows algebraically how we access these variables. So let's now go back up and look at our question and see which variable we're solving for. We're looking at vibranium-58, and what do we know? We see here 10 moles. That's what we started with. So that right there is going to be my n naught. Some of that has decayed to titanium. It gives me an amount, 0.15 moles. So that means my n is going to be equal to my n naught, my original amount, minus what was lost to titanium, which is 0.15. It tells us in the question we're solving for half-life, so time elapsed should be in here. And indeed, what do we have? We have 1939 to 2018. That's 79 years. So t equals 79 years, and we're solving for t half. And following the algebra that we just did previously, our equation for t half looks like this: negative 0.693t divided by the natural log of n over n naught. So now it's just a matter of putting in the numbers. T, we said, was 79 years divided by the natural log of n, which we said n was the original 10 minus what was turned into titanium, which is the 0.15. So 10 minus 0.15, which turns out to be 9.85, divided by the original, which is 10. So let's replace this so you can see it. And again, because both of these were moles, those cancel out. And now it's just a matter of putting in the calculator, doing the math. And what do we come up with? If we did it right, 3,622 years as a half-life for our imaginary vibranium. So hopefully that helps you understand how to manipulate the equation to solve for the variable that you want to solve for. It's pretty straightforward. And the trickiest part is just understanding the relationship between the natural log and the natural base, ln and e, and how they're inverse of each other and essentially cancel each other out.